All right, welcome everybody. Today it's my pleasure to introduce Jeff Boschert. Some of you I know for your point papers, you looked at some articles that Jeff had, and he's going to talk he's coming to you from St. Louis. Normally he comes out to Arizona, but unfortunately with this COVID and travel issues and all that, he's coming from St. Louis, but at least he's gracious enough to talk about vitrified clay jacking pipe and different technologies and particularly pilot tube technology, which I think he's one of the most experienced people in terms of seeing a lot of pilot tube technologies in that. Jeff is the director of the National Clay Pipe Institute, and here in Arizona, a company called Building Products near downtown Phoenix is a pretty big clay pipe manufacturer. And it's a pretty interesting process to see. I visited there a few times. I've seen how they build these pipes and that. I think it's quite fascinating. So with that, and one thing with Jeff is when you have questions, please just unmute yourself and ask away the questions. That would be the best way, rather than typing them in the chat. I mean, let's try to make this as interactive as possible. So if you have a question, just unmute yourself and just interrupt him, and he'll answer the questions for you. And that I think that's the best way to go that way. So, anyways, with that, Jeff, why don't you take it away? I'm going to put myself in mute and go ahead.
Hey, thanks, Dr. Sam. Again, I'm Jeff Boschert. I'm president of the National Clay Pipe Institute, and well, not building products, but one of our manufacturers in Ohio makes it's a specialized jacking pipe made out of vitrified clay. So that kind of got us in the trenchless world. Started in about they started making that pipe in about 1992. So we're predominantly used in a technology called pilot tube guided boring, and which we're going to get deep into today. Also doing it for several other methods. Microtunneling is one of them. We're going to cover a little bit of that. But I guess what's made there in Arizona is conventional bell and spigot pipe for open trench construction. And if anybody was ever be interested to do a plant tour there, let me know, and I can get you guys set up for possibly a group tour of the facility. Hey, with that said, let's get started. But again, I want to reiterate, if you have a question, just interrupt me and ask. I'd rather take questions as we go. If you were unclear on something on what I said or what I showed on the screen, let's ask it, and we can have a discussion and possibly make this this virtual platform a little bit more interactive. So we'll get started with the pilot tube method of guided boring. And in your point papers, you might have seen this different terminologies describing what is really the same method. And there's been many names over the past 25 years for this technology. Initially, they called it pilot tube microtunneling, or the acronym PTMT. One manufacturer of equipment calls it guided boring method. Another one calls it guided auger boring, or some people just call it the pilot tube method. And oftentimes these terms are confused with one another, but they're all the same exact technology. We spent about 4 years drafting an ASC manual of practice, and we published it in August of 2017. And we went round and round with what to call this thing, and we settled on, there's a picture of it on the screen, we settled on pilot tube and other guided boring methods. It's probably a 90-page manual published by ASCE, but I was one of the principal authors in this manual covering this technology. Hey, I'm going to start with a video. This is one of the original videos. It was done by Boschert. They're a German manufacturer of equipment, and I've got many videos throughout this whole thing. This one I think it's 7 or 8 minutes long, and I'm going to play it now. And I don't need to talk because there is sound.
Pipe jacking and microtunneling has been proven throughout the world as an economical and environmentally sensitive method of installing underground services. The guided auger boring systems from Boschert, which are shown in this presentation, have been successfully used on many continents, with more than 150 systems currently in use worldwide. The advantages of this technology are obvious, especially in towns and cities, where utility services can be installed underground without disrupting traffic flows or interfering with daily life. The special advantages of the guided auger boring systems, like the quick setup times, minimum site facilities, high jacking performances, simple operation, and low capital investment, can combine into a highly profitable operation, which has been demonstrated worldwide by the installation of over 300,000 meters of ducts and drains. The following sequence shows the laying of a 400 mm diameter sewer in a residential area using a Boschert BM400 with double-walled pilot rods and groundwater auger. The sewer is to be installed 4 meters below ground level and below the groundwater table from a working shaft of 2 meters diameter. Traffic is unaffected, and the new line can easily pass beneath existing services. Damage to the roots of trees and bushes is avoided by the use of this method. Work on site commences with the construction of the launch and reception shafts by the caisson sinking method. The precast concrete sections are sunk into the ground as the soil inside is removed by the excavator. To avoid ground loss, the water level inside the shaft must always be higher than the water table in the surrounding ground. When the shaft has been sunk to the required depth, the concrete base is placed underwater. The compact site setup consists of the boring container, the hydraulic power pack, and racks for the pilot tubes and auger casings. After positioning the boring container above the launch shaft, the crane is extended so that the BM400 machine and base frame can be lifted out of the container by the 2.5-ton hoist. The cover boards are removed from the floor opening and used to form the guardrail around the top of the working shaft. The base frame is first lowered into the shaft and easily set for height, grade, and line before being braced in position. The BM400 is then placed on the base frame and fixed in position. Use of the base frame simplifies the operation and eliminates the difficult time-consuming job of aligning the boring machine. After the machine is set up, the guidance system is installed. The theodolite with its electronic camera is mounted on a height-adjustable support, independent of the machine. The theodolite is set to the required height, grade, and direction. A monitor screen fixed onto the wall of the shaft allows the operator to view the target through the theodolite-mounted camera during the piloting operation. The first step is to install the pilot rods. The double-walled pilots consist of a pilot head with an integral LED target, an outer screwed casing, and an inner pilot rod. As the pilot is advanced, the camera on the theodolite can view the LED target on the pilot head through the hollow pilot rods, and the crosshairs on the monitor screen indicate the correct alignment. By rotating the inner pilot rods, the operator can turn the pilot head to use the inclined plane at the front to correct any deviation from the intended line or level. The pilot head is pushed out of the launch shaft through a flexible seal and into the soil. Pilot rods are added and jacked into the ground. The pilot rods are jacked into the ground without rotation, but if any deviation from the intended alignment is visible on the monitor, The jacking is stopped and the pilot head is rotated to correct the deviation when the jacking procedure continues. The inclined plane on the pilot head creates a reactional force from the surrounding soil to achieve the steering correction. When the pilot head arrives on target at the reception through the seal, the pilot rods with the pilot head are disconnected and lifted out of the shaft. The pilot rods are then followed by a reamer coupled to steel casings with augers inside. The ground is excavated by a special cutting head on the reamer and transported by the augers back to the muck skip in the working shaft. The reamer with the groundwater auger is connected via steel arms with the pilot rods. The special cutting head works behind the steel arms. In the case shown, the reamer is designed as a groundwater auger. In the first steel casing there are two bulkheads, each with openings in the lower area. The auger in this casing also has two bulkheads, with their openings 180 degrees apart. Thus, only one pair of openings through the bulkhead walls is open for the transport of excavated material at any time during rotation of the auger. When the back bulkhead is opened, the front bulkhead is closed. When the back opening starts to close, the front one starts to open, and vice versa. The excavated material that is conveyed out by the augers falls into the muck skip in the working shaft. After the completion of each boring stroke, the muck skip is lifted out of the shaft and emptied before the next casing and auger put in place. When the reamer reaches the reception shaft, it is disconnected and lifted out. If product pipes to be installed have the same outer diameter as the casings, then the first product pipe is coupled to the casings in the launch shaft and jacked into place in the third step of the operation, like the clay pipes in this example. During this operation, the jacking force only has to overcome the skin friction. As the product pipes are jacked into place, the augers and casing are disconnected and lifted out. When the last casing reaches the reception shaft, the jacking procedure is completed. After an inspection, the sewer can be commissioned. If a sewer with a bigger outer diameter is to be installed, a second reamer enlargement is used for the third step. In the launch shaft, a reamer with a direct drive unit is coupled to the last casing. The product pipes are pushed in directly behind the reamer. The drive unit in the reamer is powered through hydraulic lines that are laid through the following product pipes. The ground is excavated with a special cutting head and transported through the steel casing to the reception shaft by the anti-clockwise rotation of the augers. The excavated spoil is removed from the reception shaft. When the reamer reaches the reception shaft, the sewer is complete. The process technology shown in this presentation makes it economically possible to achieve the benefits of trenchless technology, where previously open-cut trenching methods, with all the disruption and disadvantages, would have been used.
Yeah, that's a it's a pretty good video that they put together. Back when it was sort of in its infancy stages, this method. But I guess as you can see, this method is it's highly accurate. It's a guided system of tunneling, and because of the kind of accuracy that it has, it's primarily used for gravity flow pipelines, but it doesn't have to be. The video showed sort of the generic method, which is pilot tubes, and then the reaming head and thrust casings, followed by the product pipe of the same size. And then they also showed there at the end, if you had a larger diameter product pipe, to go in with a powered reaming head. But the accuracy of this system is about 1/4 inch and 500 feet on line and grade, and the way it steers, there's no ups and downs. It's a rifle barrel. But the construction, of these projects begins with the installation and building of the shafts. 8-foot round is the smallest jacking shaft that you could have, and it's pretty common, 8-foot round pits, and they're dug with an auger rig. On the left side of the screen, this is an auger rig excavating a shaft. Commonly, if it's an 8-foot shaft, they're gonna excavate a 9-foot hole in the ground. So this is a 9-foot diameter auger. This is a 9-foot diameter rock bucket. And then if you've got a round shaft, it has to have a liner of some sort, either a steel casing or corrugated metal pipe. On the left side, this is an 8-foot diameter corrugated metal pipe. So what happens is they've got this 9-foot diameter excavation, then they drop an 8-foot CMP pipe down to the bottom as a liner, and then there's a 6-inch annular space that can be filled with flowable fill or just crushed stone, what they would fill that with. And then you can put what I call a round jacking frame in there, and you can punch out of that thing with your installation in any direction. The photograph on the right side, it's a telescoping trench box, if you will. And that one, I think, is an 8-foot wide, 10-foot long for more of a square type jacking frame. This is a video of a shaft installation. I think it's a video of, they've already dug the shaft and they're dropping the liner down to the bottom.
Okay.
This is another round shaft, larger size, but this was a deep shaft on a project I was involved up in north of me in Milwaukee. But this is what they call a ring beam and wood lagging shaft, and these are constructed. They dig down and construct another ring and keep going down. And this one was about 45 feet deep, dug with a long arm excavator and then a mini excavator in the bottom. But this one, I think, is a 12-foot diameter on that bottom section, and they've tunneled out three different runs out of this. This is a jacking pit. They're jacking 18s down to the bottom of the screen, and then 18s went to the right, and then up on the top side right here, this is an 18 or 15-inch line going this direction. So the 15 comes in, this 18 comes in, and then it all flows out to the right side. Again, shafts, 8 foot's common on the smaller diameters and short lengths, 8 by 10 or 12 foot. These are probably the 3 most common shaft sizes with this process. Really the shaft size all depends on the frame and the section lengths that the contractor would want to push. but this is just it's 5 different jacking frames that are on the market, and these range in capacity from about 100 tons of thrust capacity up to about 275 tons on some of the bigger ones that are in the marketplace today. So you saw the video. I'm going to kind of go through the same thing in slide form to really talk about how this method works. In generic form, the soil conditions have to be displaceable, because in the first step, they're pushing this pilot tube, which is a 4-inch diameter. It's a hollow steel tube, and that's getting pushed through the soil, and the ground is being displaced. Now, what controls the steering is this slant face steering head that's rotatable, and the guidance happens. There's an LED. It's a battery powered illuminated target that's housed up inside this steering head, and the image of this target is transferred through these hollow steel pilot tubes through a camera that's mounted on top of a theodolite and projects on this monitor screen. So, the operator, as he's advancing pilot tubes, he's got a real-time view of the exact position and head orientation of the steering head. And if there's any deviation from from his intended line, and he keeps going, it could create a dog leg, if you will, in the run, and then he would lose his target. So, they never go forward blind. It's always a perfect shot from one end to the other. But in this first step, is where all the guidance happens. They're advancing this pilot tube, again, 4-inch diameter. The section lengths are commonly 30 inches long, and they thread together. And so in this first step, they're advancing the pilot tube from one end all the way to the other. And it's sort of a probe, if you will. It's different than other forms of trenchless technology. If they hit this obstacle between the jacking and the receiving shaft, and they may not know what it is, and they say, okay, I've hit this obstacle, we can't keep going, we can't dig down because of whatever is on the surface above. Can we they can always pull back and decide, they could change their line, they could change their grade to possibly miss whatever they've hit, which is kind of a unique feature of this technology. The other thing that's kind of neat too is when they reach the receiving shaft, where they've established the center line of the bore, whether it's an 8-inch diameter bore, final bore size, or a 48-inch diameter final bore size, they can shoot line and grade on the pilot tube, and they're going to know the exact position and alignment of their proposed tunnel before the pipe's ever installed, or before they're really committed. Because there could be a bust in the survey or a bad setup of the theodolite and or the jacking frame, and realize, hey, we're a foot off on grade at the receiving shaft. They're in this stage of the game where the guidance happens, they're not committed. So they can retrieve all those pilot tubes, they could pull it all back and change their line or change their grade or whatever the error is. And so again, differently from other forms of trenchless, where all this guidance happens, the contractor's not committed like he would be in a big tunnel or microtunnel or an MTBM that's been installed. Again, for displaceable ground, there's several different angled steering tips that can be put on. There's a 30 degree, a 45 degree, and a bullet. It all depends on typically the SPT value or blow count values of the soil that they're tunneling through. These are 3 images of the components of the guidance system. This is it's typically a standard theodolite, and then you can see this section on the back. This is the camera. So this camera is transmitting the image of this target. This is the target right here, battery powered LED target. This camera transmits the image of this target to this monitor screen. It's a computer monitor screen that the operator is viewing as they advance these pilot tubes. And the whole goal is to keep the center LED in the center of the crosshairs. And this straight line here, same as this one over here, that's the direction of the slant. So theoretically, as they advance forward, you know, that tip is going to move. Like if you look at this image of the screen, it's gonna run to the top left of the screen, and they're going to rotate. And so the whole goal is to keep this center LED in the center of the crosshairs as they advance. This was a project I was involved in, and I climbed down and got a picture of the digital readout of the theodolite. So you can see the top there, that's the vertical percent. This is the slope. So in this particular drive, they were going downhill, hence the negative sign. They were going downhill at a 0.5% grade. And then beneath that is the horizontal alignment, and they've got that theodolite locked in at 0. So, you know, before they push, they would set up this theodolite on that intended line, and then the grade, whether they're going uphill, they're flat, or they're downhill, is dialed in digitally. So this is what the operator is looking at as he's installing the pilot tubes. And you know, it's really a simple process. You can see at the bottom right of the image, you can see the theodolite here, and this has a line through these hollow steel tubes all the way to the tip. And he's got his monitor screen here, and he's really got two controls. He's got a thrust forward or pull back, and then on his other hand, he's got a rotation. So, you know, he's watching that screen as they're advancing these pilot tubes. Again, it's a real-time view, you know, from every inch of the push. Okay, here is just a summary video of this first step.
Step 1 in the guided boring method is the installation of the pilot tubes on line and grade. The 4-inch pilot tubes are pushed through the ground from the launch to the reception shaft. The leading end of the pilot tube is the angled tip steering head. This head holds the LED illuminated target that is visible through a theodolite, camera, and monitor. The theodolite and digital camera are set on the desired line and grade and positioned to view the target through the center of the pilot tube. The crosshairs of the theodolite are visible on the monitor along with the illuminated target. The operator rotates the steering head as needed to maintain the desired line and grade. By using a computer monitor and digital camera to view the output, the signal can be digitally enhanced, allowing for an extended run. This guidance system has ensured line and grade tolerance of 1/4 inch in distances exceeding 500 feet. The dual-walled pilot tubes provide a means to lubricate the outside of the tubes as they pass through the ground, which reduces the force required to thrust and rotate during installation.
Yeah, I just can't stress enough how accurate the system is. This was it was a photograph taken. This was an existing manhole that they were saving, and the contractor, this was his second drive. He rented the equipment, and he was tunneling. I think it was a 12-inch pipe into this existing manhole. So he set up a jacking pit, and then he sent a crew down at the receiving shaft, which was again this existing manhole, and they cored a 6-inch diameter hole in this manhole, and to accept the pilot tube. And this was back in 16, but it was a 280-foot shot from the jacking pit to this existing manhole, and you can see how accurately they hit this hole that they cored. The steering head, this particular one, was a 5.5-inch diameter head. You know, behind that was the 4-inch. It's actually about 4 1/8-inch OD pilot tube. Okay, this is the second step, kind of like you saw in that first video done by Bortec. So again, the pilot tubes are installed from one end to the other. That was the completion of step 1. And then step 2 is they install a reaming head, and followed behind that are auger or some people call them thrust casings. So at this stage of the game, they're taking on spoil. So the spoils around the displaced ground, if you will, around those pilot tubes would enter this reaming head and then be augered back in typical auger bore fashion back to the jacking shaft where it's removed. The earlier video you saw, they showed they had a muck or skip box down within that frame. When it gets full, they have to pull it out and unload. Some of the guys here around the country, they use a vacuum truck, and they send that 4-inch vacuum pipe down to the bottom, and they just vacuum it out as they install. Again, all the guidance equipment that you saw in the first step slides, all that comes out, because once the pilot tubes are in, everything else that goes in behind them follows that same on grade path. So at this second step, there's a crew at the receiving shaft. As they get a full stick of pilot tube enters the shaft, they take it apart, and it comes out. And then there's a crew at the jacking shaft end installing these temporary augers and casings, and then taking spoil out at the same time they're pushing. The two common sizes for reaming head and auger casings behind the pilot tube are 11-inch OD and 16-inch OD are the two standard sizes that are made. These are both 11-inch OD reaming heads. There's a couple different styles. The top one is I'm going to call it a cookie cutter or knife style head. The only rotation happens inside of that, up inside inside those 4 fins. The one on the bottom, this is more of a cutter style. So this style here, it would rotate the pilot tubes as well if there wasn't a swivel in place. But what dictates which head to use in step 2 is how tough that ground is, and if there's any kind of cobbles or boulders or anything anticipated in the soil. But these rotational cutter type heads, they have to have a swivel in place. Otherwise, they're going to, that machine would have to rotate all those pilot tubes as they rotated all the augers inside these casings. So, there's a swivel adapter that would go in. A picture of those is on the right side of your screen. But this would be in place. It would attach to the last pilot tube and to the front of one of these cutter heads. These reaming heads or cutter heads, they have lube ports in them, and depending on the soil, lubricant may be necessary either in the pilot tube or in step 2. And these reaming heads have ports. You can see the arrows. This arrow right here, if you can see my cursor, this would lubricate the OD of the casings. And then there's lubricant ports here, and a lubrication here, it would help ease the soil transfer through those augers and casings. But in order to hook up a lube line to that reaming head, this is a picture in a receiving shaft. So they've already installed these pilot tubes, and they would send, it's commonly a 3/8 inch diameter line. They would send this line through that hollow pilot tube, because they don't need that hollow path anymore for line and grade. The grade's already been established. So they would send this through the hollow center of the previously installed pilot tube, and would hook on to it'll hook onto the front of one of these reaming heads, because this is installed directly behind, and provide path for lubrication of for friction or for lubricating the spoil inside. Here's a couple of shots of thrust casings that would go in behind the reaming head. Again, these are either 11-inch OD or 16-inch OD. The bottom picture, the bottom left photograph, those are 16-inch OD, and the one on the top, that's an 11-inch OD. thrust casing, and these are, again, these are specialized casings. They don't weld together. They've got clips. They would clips that would hold the casing to one another that get installed. There's sort of a spigot and a bell end on these things, and then the auger bolts together. You can see the bolts here to bolt those augers together, so they can be installed fairly quickly. Put the clips in, and then when they're dismantled at the other end, they pull the clips out and take them apart. Okay, here's a video of step 2, what we just talked about.
Step 2 is to increase the bore diameter by following the pilot tubes with a reaming head that matches the diameter of the final product pipe. The reaming head and temporary casings and augers are attached to the pilot tubes and advanced by the jacking frame. As the temporary casings advance, they push the pilot tubes into the reception shaft, where they are removed. Spoils are removed and transported by the augers back to the launch shaft and fall into a dirt bucket, which is emptied when full.
Okay, the final step, and this is the generic process where the OD of the final product pipe matches the OD of the auger or thrust casings installed in step 2. And you know, again, the 2 most common sizes for those casings are 11 OD, and for a clay jacking pipe, that's an 8-inch ID jacking pipe has an 11-inch OD. So that's the size. When 8s are installed, it's always done this way, size on size. So 4-inch pilot step 1, 11-inch auger casing in step 2, and then 8-inch jacking pipe in step 3, and then they're done with that drive, or 12-inch. And the OD of 12-inch jacking pipe it's like 15.9, so they would use the 12-inch would follow directly behind the 16-inch OD size. But in this step, you know, the load on the jacking pipe is solely the frictional load to push those casings into the receiving shaft. So all they're doing in step 3 is replacing the casings with the pipe. Here's a shot here. These are 12-inch pipe, and he's got a larger shaft here. Actually stores some pipe in the bottom of the shaft. But so these are 12-inch 1-meter sections of jacking pipe, and they're advancing 16-inch OD casings, 1 meter sticks of thrust casings out to the other side. There's a crew at the other end taking those apart. Video to sum up step 3.
Step 3 is the installation of the final product pipe. A pipe adapter is installed on the last section of the temporary casings and augers to match the final product pipe. Just as the temporary casings and augers replaced the pilot tubes at the receiving end, the final product pipe pushes the temporary casings and augers into the reception shaft, where they are removed. The process is finished when the product pipe reaches the reception shaft.
You guys, I like a lot of videos. I think maybe it grabbed the attention more, but here's another video. This is one I shot. This was a project. I live in the St. Louis area. This is one not too far from my house, but this is an 8-inch pipe, 1 meter, and they're assembling those pipe sections. And this is in that 3rd step, and they're pushing out 11-inch 1 meter long casings into the receiving shaft. So this one here, you're going to see the guy lubricates the joint. He homes the pipe. You're going to see a line. They've got a line running inside the pipe, and it was a loop port at the tail end of the casings. They never did hook it up. They were worried their pressures would go high, pushing the product pipe. So they had it just in case to lube if they needed to. That's that lube line. So he's lubricating the inside of the bell, if you want to call it a bell, on that pipe and then lubricating the spigot. So they use the jacking frame to home the joint.
See what I mean, Jeff?
So as you can see, you know, this is the third step. It goes fairly fast. It goes as fast as they can lower pipe section, get it mated up, and there may be some delay on the other side because he can't push another section until they get the crew at the other end, you know, takes the auger and casing apart. It's a fairly fast process. Hey, the first video I showed, there at the end, it showed a powered reaming head, but there's also powered cutter head. So this is a video that kind of shows both, and then we're going to get into those and kind of how those work.
The powered cutter head still uses the three-step GBM process. As previously shown, Step 1 installs the pilot tubes on line and grade. During Step 2, a reaming head and temporary casings and augers are attached to the pilot tubes. The powered cutter head is added in Step 3 and is used to increase the bore to match the final product pipe diameter. Final product pipe is added behind the PCH. The direct drive at the cutter face allows the GBM to work in a wider range of soil conditions while maintaining speed and accuracy. The augers are reversed by the PCH's hydraulic drive, and the spoils are pushed to the reception shaft while the rotating head cuts the tunnel to the final diameter.
Okay, so the powered cutter or reamer typically is for larger diameter pipes. When, you know, the final product size is bigger than, you know, either the standard casing size of 11 OD or 16 OD. So they would couple on this powered cutter or reaming head and take on the additional spoil, enters the front of one of these heads, gets turned around inside, and then sent forward through the augers. The augers are reversed. So this additional size that they're cutting on the bore gets sent to the receiving shaft, along with the thrust casings installed in Step 2. And these are some of the common sizes. There's a 20-inch, a 22.5, and a 28.5 powered cutter, and then there's two larger sizes, a 36 and a 44 OD. Here's one here on a project I was involved in. This was a 22.5 powered cutter, but you can kind of see the close-up shot of that. So, you know, looking at the front of that powered cutter head, you can see what looks like the spigot end of one of those 11-inch OD casings. So that would, you know, they would lower this section down, and it would hook up to the last casing installed in Step 2, and then the jacking pipe would advance this unit because it's the same OD. And so this thing's doing two things. It's got a rotational cutter spinning that's cutting this additional ground from the 11 OD up to 22.5. And then there's 4 windows in this particular one. So as the soils are cut by these picks, it would enter the head and then get turned around inside and then sent forward through all those casings installed in Step 2. Again, all while being advanced by the product pipe. So here's a tail end of that same unit. So, I'm gonna cover the jacking pipe at the end, but the back of one of these units looks like the bell end of one of those jacking pipes. So the spigot would mate right up to the back of this and advance that forward. Here's a video here. I took this at a demo. I forgot where, but these powered cutters, they've got jets in the front to ease that spoil travel. So this was one. You can see how this thing drives. That one there is a 36-inch OD unit, but you can see, that's got several drive motors in it. One or two drive the powered cutter itself, and then the other one, it powers the auger inside in that reverse direction. This is a shot here. This was I think it was a 10-foot round, maybe it might have been a 12-foot round caisson shaft. And that's a powered cutter down there that they've lowered down. That was the initial push for it, and I think it was a 22.5 as well to push. It was an 18-inch diameter jacking project. But what I didn't mention, and you saw it in the video, but whenever there's a powered cutter or powered reamer project, something's got to drive that unit. And, there's hydraulic lines that have to be snaked through the jacking pipe. And so commonly they stage the pipe at the surface with the hydraulic lines already mated inside of them. And then they've got to lower those pipes down with the lines inside to keep going. So here's a video of lowering one of those pipe sections. This one's a 2 meter. I kind of forgot the size. But again, whenever one of these is used, remember the spoils are coming to the reception shaft at the same time the augers are. So the guys at the receiving shaft are really doing double duty. They're dealing with the spoil, number one, as well as once they get a full stick of casing and auger, they've got to take it apart as they're pushing pipe. There's also the powered reaming head, which is really what that first video showed. This is the same concept as the powered cutter, except it doesn't have this wheel in the front to cut soil. And these are commonly available from 14 OD to 20-inch OD. And this is what they look like. It's more of a knife style or cookie cutter type unit. And but it's the same concept. The spoil enters the front of that unit, and then it gets turned around, and then there's a drive unit in there to turn those augers the reverse direction as they're installing. But this is a 14, 16, and 20 OD, all size for 10, 12, and 15-inch ID clay jacking pipes. That's what the sort of a close-up shot of the front end of one of those units looks like. A couple of job photos here. This was a powered cutter head project, all out of an 8-foot round shaft. And you can see the hydraulic hoses that are snaked through the jacking pipe, and then once it's lowered down, it's got to be mated up and then ready to push. This is a shot of a powered reamer. This is I think it was a 15-inch project. So this is a 20-inch OD powered reamer. And on the front here, this is a 16-inch OD casing. So they only had to go a little bit larger to push these. So there's the 15-inch jacking pipe. That's a 2-meter stick. But again, that pipe is advancing this powered reaming head unit. Here's a shot here of a reception shaft, 8-foot round. This is the 22.5 for 18-inch pipe, 22.5-inch powered cutter head being retrieved. But again, notice the muck box in the bottom. You know, these guys were dealing with the spoils as well as the casings, and this is the final step here of the pipe pushing that powered drive unit, powered cutter head unit into that receiving shaft. Hey, there's another process I didn't talk about yet, but you know, it's called the, you know, what I just showed was the conventional 3-step with the size on size jacking pipe to auger. And then I also showed the increase technology where you've got, or in that 3rd step, you've got a powered cutter or powered reamer that have a larger diameter jacking pipe. But this is another methodology for going larger, and it's called the 2-pass, or some people call it the 2-phase method. And just quickly how it works, you've got the, you know, again, the first step is the same. It's a line and grade establishment with the pilot tube, you know, guided by the theodolite. And behind that, for a 2-pass method, would be a reaming head that's sized to the OD of our jacking pipe. But within that reaming head, the spoils are necked down to a smaller diameter auger that's housed inside the jacking pipe. So they call it the 2-pass method or 2-phase method, because in step 2, you know, they're removing the spoil and jacking the pipe in at the same time, and the pipe advances this unit. So this is 2 different projects, but the photographs on the left, that is the same head, but that's a 2-pass or 2-phase reaming head. So, you know, again, up here in the front, this would mate to the lastly installed pilot tube, and this thing is sized to the OD of the jacking pipe. And then here's the back of that unit. So the back of this unit, you've got the jacking pipe mating up to the OD, and then you've got this smaller size casing inside of it. So, and then this is again a different project, but this is jacking pipes ready to be launched. But these have a casing already fitted up inside. So again, the second step, they're doing both. They're making the hole big enough for the pipe, they're pushing the pipe, and then they're sending the spoils back inside the jacking pipe through this temporary casing. And then here's a cross section of what one of those heads might look like. Again, pilot tube hooks on right here. They've already got their line and grade. The pipe hooks on back here. And then these augers are housed inside the new pipe, and the pipe's pushing the head, and the augers are being rotated by the frame. But again, you know, the spoils are getting necked down to a smaller size. So, you know, imagine if there was a cobble, you know, that could get hung up right here. There could be an issue with having to neck down those spoils. This is one of the project I was involved in. This was in Ohio, but it was a 24-inch, so that's a 30-inch OD unit. And again, you can see how it just necks the spoil down. And this was a 30-inch unit. This is a 12-inch or 11-inch auger right here. This was an 18-inch project with 2-pass. So if you look real close on the screen, you can see the guys, they've lowered the pipe section, and you can see this auger and casing right here. They're mating up that auger, and then they're ready to slide the pipe forward to advance and then turn those augers inside the casing. This was probably the most recent one we've done with this technology with the 2-pass, but it was a 36 OD with a 2-pass head. That's the head right there being hooked onto the pilot tube. And a close-up shot in there, you can see how the material is getting necked down. And then it's kind of a wild looking shot right there. It was the contractor made this head, and again, 36 OD, 30-inch ID jacking pipe, advancing this thing. So you can see the the amount of volume that they had to auger back, just because of the sheer size of the OD of the jacking pipe. And these were the legs that they fixed to the casings, because they got to be centered. You know, these casings have to be centered inside the pipe. There's the first section of 30-inch jacking pipe. That's a picture there of looking down in the shaft, pushing those 30s. I guess I'll say one more thing. This is the end of that two-pass, discussion. But really the advantage of the two-pass is, the contractor, he'd only have to invest, in the frame, pilot tubes, and say he bought 11-inch augers, he could buy a couple different size two-pass heads, and be able to install multiple pipe sizes for a project or projects, just by buying a different sized two-pass head. So that's the advantage for the contractor. The disadvantage is, necking down on the material and having a possible problem. I took this picture. This was kind of a situation where the contractor, he pushed his pilot tubes, and he got into some harder ground and some situations where it was pushing him off line and grade. And so it took him a bit to get the pilot tube in, but he was successful on getting it in from one end to the other. And I kind of forgot the pipe size now that he was going to, but the contractor, he elected to build this missile. I'm going to call it a missile. It looks like tail fins on a missile, but he took this steel, I think it was half inch thick steel, and he welded these fins on this pilot tube. And what he did was, this was sort of an insurance policy for him, because he was going in with a reaming head that was sized to this measurement from this edge of this fin to the edge of this fin over here. So what he wanted to do was, he wanted to cycle this pilot tube through, because he already had this probe rod or pilot tube brought in from one end to the other. And he built this missile and cycled it through, I think 3 times before it came out the other end, with no bent fins. So really what he was wanting to do was, break up any of that hard soil around that pilot tube, and ensure he could get through with step 2. But I think if they got stuck, it was a no dig. I kind of forgot what they were going underneath, but it was not an option to dig down. So he built this missile to travel through there. But again, he cycled this through, meaning he launched the missile, and he had a crew taking pilot tubes out and they brought them from one end to the other, and he cycled this missile through to break up the soil. This is the soils chart. This is within that pilot tube MLP number 133. I'm not going to go through it in detail, but this is sort of the applicable soils chart for pilot tube guided boring. And there's really 3 limiting factors to the technology for the displaceable type soils, which is what we discussed up till now. Typically it's up to 30, no problem for blow counts, but if you get up to 50, you can do it, but maybe you can't go as far. But if you're above 50, it's really too hard to displace. So that's limiting factor for the displaceable methods, which is 95% of what we do. The other marginal soil type is, if you have these cobbles and boulders, and something that would stop the pilot tube or stop those augers and casings. So that's limiting factor 2. And then, the water table. And, that could be a definite limiting factor to this technology. Imagine if you had 25 foot of head of water, and you had a sand or a silt or something that would flow. Step 2 is really an open face auger, and the threat would be over excavation. You don't have this closed off pressure balanced head on the front. You have an open face auger. So where that water is in relation to the bore and what the soils are, that could be a limiting factor as well. There's other technologies that work better when you've got a high head pressure of water and flowable type soils. Hey, we've been on for an hour. I think I got about another 15 minutes of some of the variations with the technology, and then we're going to take probably a 20-minute break. So let's keep going a little bit longer. So pilot tube rock drilling, and this is probably all this happened within the last 5 or 6 years. They've got into some rock drilling with this pilot tube technology. And you know, these are some of the rock bits. Again, this would take the place of that slant faced steering head. And this is a pilot tube frame with a rock bit on the front. Now it's still going to house that battery powered LED target up inside. And then this is a video of going in with a rock, with one of these rock drills. And again, they're not displacing the soil. They're cutting it, and then the cuttings are being blown back into the jacking shaft. So here's a video of going in with one of these rock drills. But anyway, you know, the way this works is they're rotating to cut, and but then they're actually guiding it. You know, they can still guide it, change directions. They can still guide that thing on line and grade because they've got the same theodolite camera, LED target, monitor screen. But they've done up to about 12,000 PSI rock, or if you want to call that soft rock, you could. Here's a couple of shots here from some of this rock drill that they've done here across the country. Again, this one, I wasn't on this project, but the bottom left here is they were going into this existing manhole, and I think the guy thought he had one more pilot tube to go, and they didn't realize it, but he did, and he was up against the manhole wall, and they actually cored right through. You can see this is the front of that rock bit that's penetrated the manhole. And then this photograph on the right, this is the installed casing that went in behind the step 2 cutter for the rock cutter. Another shot here of, you know, some of this hard ground rock drill equipment. This was a sort of I think it was some kind of a red shale stone that they were cutting. Again, non-displaceable type ground. Hey, this is a video. It's another one done by Boschert, the German manufacturer, and you know, this is guided boring, but without a pilot tube. And both the two manufacturers of this equipment, they make this you know, it's really guided boring, but there's no pilot tube. And what they both use is a hollow stem auger, and that's what provides that sight path to the target. And you know, this is for you know, these harder you know, not as hard as rock, but these SBT or below count values from 50 to 100. And they, you know, one manufacturer calls it the front steer, the other manufacturer calls it the eliminator. And this is a video of how that works.
The following sequence shows the laying of a 300 millimeter diameter sewer in a residential area. A guided auger boring machine from Boschert with a novel steering technology called front steer is used. The sewer is to be installed 4 meters below ground level in a non-displaceable mudstone from a circular working shaft. Traffic is unaffected, and the new line can easily pass beneath existing services. Damage to the roots of trees and brushes is avoided by the use of this method. After the machine is set up, the guidance system is installed. The theodolite with its electronic camera is mounted on a height-adjustable support, independent of the machine. A monitor screen fixed onto the wall of the shaft allows the operator to view the target through the theodolite-mounted camera during the guided operation. With the help of a steering and control panel, showing the position of the front steer, the operator can perform steering movements. In the first step, the guided drilling is performed by excavating the soil with the front steer. Hollow augers transport the excavated soil to the working shaft. The camera on the theodolite can view the LED target on the cutting head through the hollow augers, and the crosshairs in the monitor screen indicate the correct alignment. The front steer is pushed out of the launch shaft through a flexible seal and into the soil. Steel casings are added and jacked into the ground. The excavated soil is transported by hollow augers to the working shaft. The excavated material that is conveyed out by the hollow augers falls into the muck skip in the working shaft. After the completion of each boring stroke, the muck skip is lifted out of the shaft and emptied before the next casing and auger are put in place. The operator can move the steering pipe of the front steer with the help of the operation panel to correct any deviation from the intended line or level. If any deviation from the intended alignment is visible on the monitor, the operator changes the position of the steering pipe to correct the deviation while the jacking procedure continues. The inclined position of the front steer creates a reactional force from the surrounding soil to achieve the steering correction. If necessary, it's possible to activate a high-pressure water flushing system behind the cutting wheel. After arriving on target at the reception, through the seal, the front steer is disconnected and lifted out of the shaft.
Anyway, you can see, that's also, a highly accurate line and grade technology. Again, suitable for gravity flow pipeline, but it doesn't have to be. But again, the steering with either the front steer or the eliminator, the steering is a little bit different on the two different brands that are out there, but they both use that same technology for guidance with this hollow stem auger for that, to provide that site path. I'm going to talk about a few projects and some case studies, and then we're gonna shoot. We'll take a 20-minute break, and then we'll get into the other topics. So I'm going to go through these really fast because they're easy. But this was a project. I'm going to share some pictures from this one, but it was a job in St. Louis called Fifi Creek, and our depth range from 20 to 39 feet. It was all 18-inch pipe, and it was a silty clay, fairly soft, 3 to 5 SBT or blow count material, and we had pipe, supplied in both 1 and 2 meter lengths, depending on the frame used and the shaft size. This 2 photographs here. The bottom right is one of the jacking pits, and the top photo they're overlapped for some reason, but the top photo, they've got that pipe staged along the swing radius of the boom truck, and the shaft, you can kind of see the cage around it, but that was an 8 foot deep, 8 foot diameter, 40 foot deep jacking shaft, and they jacked 1 meter pipes out of that pit. This is the launch of the powered cutter head. This was again a 3-step process where step 3 was the powered cutter in the pipe, and 18-inch ID, 22.5 OD, and that powered cutter head breaks in 2, so that's the front half of that being launched. Another shot, again, same shaft. The boom truck was over here. You can see the hook up top. Again, 8 foot round pit right here. There's a shot, same shaft, pushing the pipe. Again, 18-inch, 1 meter sections. The pipe length. What dictates the pipe length is the size of the shaft and the size of the jacking frame. I think this was a jacking and a receiving pit right here. This one was a slide rail shaft, larger shaft. They were able to jack 2 meter pipes out of this pit. Another shot there, same pit. This one here, that's inside that same pit. This is pushing the pilot tubes, and you can see this is the pilot tube section here. This is the operator. This is the monitor screen, and you can see the theodolite is set up right here. It's independent of any of this jacking frame. In case the jacking frame moves, they've got this pilot tube on target. You can kind of see it here. This is the string line. That's what they use to set the the 0 line for that theodolite to get it locked in place. And then the grade is dialed. Once they have that line set, the grade is dialed in digitally. You can barely see it, but this is the pilot tube that's made it into the receiving pit on line and grade. This is, I think it's that same shaft, different day, pushing the product pipe. They were able to push 2 meter pipes out of this larger pit. But you can see the hydraulics. So they've got hydraulics. It comes out of the frame. They've got them up top, and they snake through the product pipe, and then they're snaked back down. They run through the product pipe all the way to the powered cutter head. The video here. This is pushing a product pipe. This is a different pit on that project, but this video, they're pushing 2 meter sections of pipe, but what they're pushing out the other side are 1 meter sticks of 11-inch auger and casing. So, at this stage of the game, again, they're pushing 2 meters, but they only can push half of that pipe. Then they got to wait on the crew at the other end to take the auger and casing apart or dump the muck box. So I don't know if you guys picked up on the video, but once they got that pipe hooked up, the operator, he got on the radio, and you want to make sure the guys at the other end are ready to receive. They're receiving a spoil plus the auger and casing. So, and this is what they call a latching frame machine. This one can be shrunk down to an 8-foot pit, or it can be extended. And you can see this right section here, this latches, so he can push forward 14 inches, and then he's got to unlock and bring that section forward, and then relock in place with pins, and then push again. This is same project, but this is in one of the receiving pits. So this is what the guys are dealing with. They've got spoils coming at them, as well as casings and augers. This is another project, same contractor, I think, but this was kind of a unique project. This was a what they call a sewer separation project, and this is a plan view, but this dashed line in sort of a green color, this was an existing 66-inch combined sewer. So the purpose of this job was to separate the sanitary from the combination. And what's in red here, this was all across this, they call it the Galleria Mall, but this was all across this mall parking lot. And this was all installed via pilot tube guided boring. And the designer, he had a narrow window. He had about 5 feet beneath the bottom of this 66-inch combined sewer and the top of limestone. So this sewer pipe, it was all installed 18-inch. It was all installed with pilot tube guided boring in that narrow 5-foot window. So it was the same. It was on the same design slope as this existing pipeline. This is a shot here. This was a large junction chamber that they started at, and this was, I think, 300 feet from here across to the jacking shaft was over here. But you can see this technology was used underneath all those cars. And this mall owner, they in the contract they had I think about a 2-month period where they didn't allow the contractor to work due to the holiday season. But once he got started in late summer, they saw what kind of disruption he was creating in their parking lot, and elected to let them work all through the holiday season, because it was very limited disruption as well as impact to the parking lot. But again, it was all out of 8-foot round pits. Powered cutter head coming in on the 3rd drive. But this was the impact. This is probably the neatest slide from those photographs. This is the neatest slide, but this was the impact to all those 8-foot round jacking or receiving shafts. So the contractor, he came in and he saw cut these 10-foot by 10-foot sections in the parking lot. And this was just a week prior. This was a jacking pit. They were tunneling 18-inch pipe both directions out of that pit, 25 feet deep on that project. And that's all that they heard, less than 2 parking spots. Kind of neat. Another project here. This was up in Washington. This was using a powered reaming head. It was a 24 ID 30-inch OD project. These were 2-meter sections, slide rail shaft. But again, this was powered reamers. So, as they're pushing pipe, this is happening in the jacking pit, and this is same happening in the receiving shaft, where you've got these augers and casings coming in, as well as spoil. A little bit on hybrid methods. Pilot tube is not only used to install pipe in its conventional form, it's also used in pipe ramming, as far as a method of steering. contractor will come in and he'll push a pilot tube on line and grade, and then pull out that frame, and then use a pipe ram adapter, and then go ahead and use a hammer and ram a casing in along that line and grade, in cases where the conventional pilot tube wouldn't work or the railroad wouldn't allow it. A lot of times the railroad will want a ramming technology used, for fear of over excavation under a track. So they'll oftentimes specify a pipe ram, because there's no way that they could over excavate and have a settlement issue. So it's used, to steer make it a guided pipe ram. Probably more oftentimes than that, it's used to guide regular conventional auger boring machines. Because your typical auger boring, it's really unguided. There's about a 1%, accuracy for a conventional auger bore. So, picture a 300-foot push and 1%, going by that 1% rule, you could be 3 foot off in that 300-foot drive. And, for a gravity flow pipe, most of the time that's unacceptable. Or pilot tube, a 1/4 inch in line and grade, here, this would be your accuracy, of this casing, whatever size that may be, by having a pilot tube guide in the front. I don't know where this picture came from, somewhere in Texas, but that ram, or that auger bore came out of the ground, because it's unguided, but it would drastically improve the accuracy. You could actually go longer drives and reduce your casing size, especially with a gravity line inside, and faster installation. Hey, how can that be? You're adding a step to this conventional auger bore, but it's commonly faster because they can push the casings faster. They don't have to worry about trying to steer it or trying to trip all those augers out to make a steering correction in the front casing. And if there's an obstacle to be found, you could possibly find it, or most oftentimes you would find it before before they've even had the frame in position. This is what it may look like on one of these projects. The guided boring frame or pilot tube frame would go on the tracks, same as the auger bore rig, and install that pilot tube first, and then it comes out of the ground. That frame comes out of the ground, and through an adapter, it becomes really a guided auger bore with a conventional auger boring frame. This is what it may look like on an American augers rig. Again, pilot tube frame on the front, conventional auger bore behind on the same tracks. It's a video here on this process.
One of the most popular methods for GBM applications is using it in conjunction with an auger boring rig when accurate line and grade are required. An unguided auger boring rig may have failed bores, creating very costly overruns in terms of steel casing pipe and man hours. The universal adapter makes using your GBM in conjunction with all auger boring rigs a simple process. A weld-on reaming head attaches to the pilot tube and is welded to the lead casing. The Ackerman Pilot Guide rod swivel is used with a rotating cutter head in place of a weld-on reaming head to reduce thrust at the face in hard soil. By using the Pilot Guide rod swivel with a rotating cutter head, rotating and over-torquing the pilot tubes is avoided.
Hey, here's a couple of images, animated illustrations of what this might look like. So, again, step one is the same as you guys have seen. You've got this installation of the pilot tube on line and grade, again, with the target, the theodolite and camera, and then the monitor screen for the operator. And then once it's in, this frame comes out, and then, this would be a weld-on reaming head right here. And then followed by that is your conventional steel casing welded together. And these pilot tubes are pushed into that reception shaft where they're taken apart and taken out. You know, that methodology works up to about 36-inch diameter, sort of the cutoff where you can go from that 4-inch pilot to a 36-inch OD casing. When you want to go bigger than that, there's a whole lot of torque. When you get bigger than 36 inches, there's a whole lot of torque in this auger. So going from the 4-inch pilot to something bigger than a 36-inch, you know, there's a chance you could break the connection right here at this pilot tube. So going bigger than 36, the rule of thumb is to go up to say a 24-inch weld-on reaming head, and maybe one section of casing, and then this 2-stage reaming head right here to go from say 4 to 24 for the first 20 feet or maybe 40 feet, and then this 2-stage head, and then go up to your 54 or your 60-inch casing. But again, same concept. Pilot tube's always step one. So this is a one of those 2-stage heads right here. This is 24. I don't know what size that is, but you know, bigger than 42, you'd want to use this, which is the next size up above 36. This is a video. I think I'll go ahead and show this one. It's only a couple minutes. This was put together by a contractor named Kamloops. They're up in the Canada area. They did a pretty good job. But there's no sound in this one, but you know, this is a, you know, again, a guided auger bore. This is a highway crossing. But this is an auger bore contractor, a big trenchless contractor that I think they've pretty much adopted this technology. They do a lot of crossings with conventional auger boring. But they guide almost everyone now, I think, with the pilot tube. Again, step one, displacing their soil, slant-faced head. I've been through this several times. You guys ought to be experts in this, how this works. But it's really a fairly simple technology. So again, step one's complete. They've installed their pilot tube on in line and grade. That frame can come out, and then it becomes a guided conventional auger bore. Weld-on reaming head in the front. You know, the benefit to this is if there's a gravity flow pipe going inside the casing, they don't need to go as big, and they don't need to grade adjust, because they've installed this casing on the exact lining grade it needs to be, and so they don't need to go as large, and could actually be cheaper. You know, not as much excavation and not as large a casing. Anyway, that's the process. Yeah, I think this is my last project, and then we're going to take our break. But this was a project in North Omaha, and it was a big project. I think it was one of the largest at the time. It was about a 7,000-foot project, all on a single contract. It was all 8 to 21 inch, and the contractor he used a little bit of conventional pilot tube, but then he brought some auger bore rigs in, and did sort of a hybrid technology as well. But this was, again, north side downtown Omaha, Nebraska. But again, this was a whaler and sheet piles type shaft system that they had constructed. They had a wide variety of shaft types. But this is an auger bore rig, and that's a section of clay pipe up front. but they used a pilot tube machine to push the pilot rods on line and grade, took it out, and then the contractor, he made up casings to the ODs of the jacking pipe, and then used the auger bore frame to push those casings in place, as well as push the jacking pipe in and push those casings out the other side to be reused on the next drive of the same pipe size. So this is a unique shaft. This is an 8-sided shaft, like a stop sign, but all built out of those are I-beams or W shapes and steel plate. This is the manhole bottom, and again, those pipes were installed with a again pilot tube and hybrid auger bore system. This was an adapter that they made to sort of a pipe adapter to made up inside that jacking pipe to be able to push it. This one here, this is a reception shaft, and you can see this is the lead tip. This is the front end of the reaming head, enters the shaft, and again the pipe pushes all those casings out. This one here is they're working on the invert, kind of a neat shot with those are at least 2 different pipe sizes all entering that manhole. Hey, we're going to take our break because our next topic is slurry type microtunneling. We got 2 more topics, and that pilot tube section was by far the longest. Why don't we get back together? Let's take a 20-minute break, and we're going to get back on at 5 till the hour. Left. We got 2 topics left, and neither one of those is as long as that first section on pilot tube guided boring. But our next trenchless topic is conventional microtunneling, or some people call it slurry type microtunneling, and it's a new installation method as well for a new pipeline like pilot tube. It's been around longer than pilot tube guided boring, and it's probably the most expensive form of tunneling out there. But the big difference is it can handle any type of ground conditions, whether it's soft ground or solid rock, and it can pressure balance and handle high heads of groundwater. You're going to see from the way it works. When we first got into the trenchless world with our jacking pipe, most projects were slurry type microtunneling, and because pilot tube really hadn't evolved, but I think in the last 10, 15 years, pilot tube has really evolved to take over the smaller diameters, from 8-inch up to really about 36-inch. Pilot tube is cheaper and it's just as accurate, and it can handle most ground. So, in the small diameter jacking pipe world that I'm in, pilot tube has really taken over, and I'd say 95% of the jobs that we're involved with today use pilot tube guided boring. But hey, I'm going to cover the methodology of slurry microtunneling, and then talk about a couple of projects, and then we're going to get into our jacking pipe, and then we're going to finish. So I think we've got probably another 30 minutes, maybe 40 minutes, and we'll be through for the day. So getting into slurry type microtunneling, it's a process different than pilot tube. What's in the front in this illustration, this is what they call an MTBM, stands for microtunnel boring machine. And just quickly, the way it works is the jacking pipe advances this microtunneling head, and this microtunneling head is rotating, and it's cutting the soil, and there's no auger. What transports the spoil or the cuttings, what transports that is what they call a slurry. So they pump this slurry. It's commonly a bentonite water mixture. They pump it to the head, and and the spoil is mixed with this slurry, and then the cuttings or the spoil is taken back within the slurry and pumped back to the surface and then separated up top. So it's a continuing process where the front end is cutting the soil, and the soils are being transported in liquid form back to the surface where they have to be separated and then sent back down clean. And it's laser guided, different than a theodolite. It's a laser housed in the jacking shaft, and the laser projects on a target up inside the MTBM. So once one of these is launched, it can't be turned around and pulled back at all. So if they hit an obstacle, and they can't get through it, it's a dig and retrieve, or dig and move whatever it is out of the way, and they can keep going. But it's a continuing process from jacking pit to the receiving pit. How in most recent years it's evolved into, they can do curved drives with gyroscopes. They can do intermediate jacking stations, and they can do some pretty long pushes with both, and some compound curves. The parent company of Vortec, they did a pretty good video, and it probably explains it better than I could. But this is a video done by a company called Hearing Connect, and they're one of the leaders or they probably are the world leader in microtunnel boring equipment. And this is a video, I think it's 6-7 minutes, on the process of slurry type microtunneling.
Throughout the world, pipe jacking and microtunneling are becoming increasingly important for the installation of sewer pipes and service lines. The Herrenknecht AVN series introduced in this film has been deployed successfully on every continent. The advantages of the pipe jacking and microtunneling process are evident. Especially in urban city areas, pipe jacking causes minimum disturbance along the construction route, so there is virtually no disruption to the flow of traffic or any impact to the local economy. In contrast to conventional methods in such construction projects, pipe jacking and microtunneling has an environmentally friendly method and helps to conserve protected landscape areas. The following animation shows the installation of new sewer pipes within a diameter of 600 millimeters in an urban crossroad with dense traffic. The whole construction site can be located in a way that only one lane is affected. In our example, 150 meters of sewer pipes are to be jacked from the launch shaft to the reception shaft. At the first stage, the area around the starting shaft is cordoned off and the traffic is diverted to the remaining lanes. Due to the compact design of the machine and the small diameter of the starting shaft, there will only be minor disruption to the traffic flow. In this case, the start shaft consists of a round shaft of reinforced concrete with an inner diameter of 3.2 meters. The compact jacking frame is then placed into the starting shaft, and the slurry discharge pump is mounted on a platform adjacent to the jacking frame. The operating container with the control panel and a hydraulic power pack is located on the top rear side of the shaft. A pipe stock is then established and maintained in front of the shaft to feed the shaft crane. The slurry feed pump and the slurry discharge pump are connected to the settlement tank to form a closed slurry circuit. The AVN 600 machine consists of several segments. A sleeve shaft with 3 boreholes connects the cutting wheel with the drive unit. The mix of crushed material and slurry water is sucked off through these boreholes by the discharge pump. The conical crusher situated in front has reinforced crushing bars and is provided with nozzles to inject the slurry water. The sleeve shaft, which is connected to the cutting wheel, is driven by hydraulic motors. The sleeve shaft is seated in a tapered roller bearing. 3 hydraulic motors transmit the rotation via the gear rim to the sleeve shaft and the cutting wheel. Three steering cylinders enable the operator to correct the direction of the tunnel boring machine, as well as control the alignment of the machine in curved drives. Therefore, the position of the cutter head is continuously updated with the help of the laser guidance system. To ensure AVN 600 has a smooth method of excavation, the machine has 2 integrated water circuits. The standard circuit supplies slurry water to the annulus via 5 hoses fixed to the inner side of the bulkhead. Several boreholes branch off from the annulus, which supply the chamber situated behind the conical crusher. The slurry water is continuously pumped through the conical crusher chamber, sucked off through the boreholes of the sleeve shaft, and transported back to the settlement tank by the discharge pump. A second hose supplies the high-pressure nozzles used in the conical crusher. These nozzles avoid clogging and agglutination in the crusher chamber in case of cohesive soils. They cut the clay in the crusher chamber with 250 bar water pressure and consequently make material transport easier. There are also 2 nozzles that are directed to the front part of the cutting wheel. This totally depends on the geological situation, as the number of nozzles can be increased. The water coming from the nozzles is mixed with the water of the slurry circuit and the excavated material. The whole mix is then transported to the settlement tank. The cutting wheel excavates the material at the tunnel face. In the crusher chamber, the material is grinded down to the appropriate grain size by the spokes of the cutting wheel, which operates in the same principle as a coffee grinder. Large stones are crushed by the discs of the cutting wheel. Sometimes fragments are being displaced to the surrounding soil. Stones, attaining the crusher chamber through the openings of the cutting wheel, are crushed by the reinforced conical crusher and the spokes of the cutting wheel, and afterwards transported together with the slurry water to the surface. The material is picked up in the slurry circuit and transported to the settlement tank through the central slurry discharge hose. The slurry feed and discharge lines are passing through the jacking pipes via the jacking frame up to the surface. The slurry discharge pump removes the excavated material and pumps it up into the settlement tank, which consists of 2 chambers. At first, the excavated material is pumped into the rear chamber, where it settles due to gravity. The overrunning water is collected in the front chamber, from where the clean water is sucked by the slurry feed pump and returned to the slurry circuit, thus creating a closed system. The product pipes are lowered into the shaft, one after the other. The jacking frame works in 3 stages. After approximately 1/3 of the maximum jacking stroke, the jacking arms return and the main thrust ring of the jack can advance further. After jacking the product pipe, all supply lines, such as hydraulic hoses, are disconnected. The jacking frame is returned to its original position and the next product pipe is lowered. This procedure is repeated again and again until the whole drive length is completed, reaching the reception shaft. Crossing pipes and buildings can easily be overpassed or undercrossed with this technique. Thus, the machine arrives in the reception shaft exactly at the planned coordinates. The drive is continuously monitored by a laser guidance system. The laser itself is positioned in the starting shaft, meeting the laser target, which is installed behind the cutter head. The laser beam determines the reference axis. The laser target identifies any deviation which may occur. The coordinates are transferred to the steering computer in the container and visualized on the screen. Any deviations in position can be corrected by adjusting the steering cylinders at the push of a button on the control panel. The length of the tunnel is recorded by a metering wheel. This information is transferred to the control panel and allows the operator to determine the location and direction of the machine cut ahead at any time. In our example, the total of 150 meters of new pipes could be realized with only a minimum of disturbance in a sensitive infrastructure. The conventional open laying of pipes would have caused major disturbance and annoyance for traffic and the residents. Herrenknecht, being the leader in technologies for mechanized tunneling, has both the know-how and the experience to realize every tunneling project. Throughout the world, the company, with its headquarters in southern Germany, is the only supplier offering the entire range of tunneling machines, with diameters of 100 millimeters up to more than 14 meters. Hard rock TBMs, EPB machines, mix shields, and machines with partial face excavation, as well as pipe jacking and HDD equipment manufactured by Herrenknecht, successfully realize mission breakthrough all over the world and in every geology. 25 years of experience in mechanized tunneling, as well as the global service network, make Herrenknecht your competent and reliable partner.
Yeah, as you guys can see, there's some differences between this and pilot tube. You know, it's laser guidance versus a theodolite and sight path. You know, there's no auger transport. It's all taken out with slurry, and you know, with the slurry they can increase that pressure and balance any kind of a groundwater head. This is a photograph. The bottom right of this photograph is an older Iseki inside of an Iseki brand microtunnel MTBM, and this is actually a camera that gives the operator a view of this is the target right here, and he can actually see where that laser beam is hitting the target. And then there's some gauges up inside that's monitoring all the particulars of the MTBM as it's traveling. And then this is the front end of that machine. This is what they would really call an open face machine, really designed for soft type ground. And you know, there's no rollers or picks on here for rock cutting or mixed face. This is again an open ground type machine front end. This is inside of an operator. You know, the operator on a microtunnel project, he's in this controlled, nice environment compared to pilot tube where he's down in the pit. So you know, this guy's in control of the whole project. So he's actually, this video screen here, this is up inside the MTBM. You can see those same gauges here, as well as where the laser beam is, and he's controlling all the particulars of the machine, as well as the soil separation plant that's up top with him. So he's controlling the pumps, soil separation, as well as the MTBM itself and the jacking frame. This is a shot here. This is a microtunnel MTBM. This is a full rock face. You can see all those roller cutters on the front of that. So a full rock project. This one's more of a mixed face with the picks and the buttons on the front, as well as the big open areas. More of a mixed face type MTBM head. So again, you know, these things can handle pretty much all forms of soil condition. It's a guided technology, as well as can handle the water. So it's you know, this is oftentimes the least favorite, if you will, because it's expensive. But you know, oftentimes it's the only, you know, guided method that will work for the project. This is the shot here, the job I was involved in down in Atlanta, Georgia. It's a 50-foot deep shaft. It's a ring beam shaft. I think we were jacking 30s or 36s on this one, but you can see this is the end of the last pipe they jacked. This is the jacking frame. You cannot see. I think the laser is right here behind where the labor is. And these are the slurry pumps here. These flexible hoses here are getting ready to get connected in the next pipe. So they've just lowered pipe section number 38, and they're hooking up the slurry lines that are housed inside the jacking pipe. And then these flexible lines here hook onto those rigid slurry lines, again, for soil transport. This is up top. This is the shaker type separation plant. So again, this is these solids are being brought back in liquid form and then have to be separated up top. So it's a continuing operation of separation up top. There's this method's expensive just because of all the equipment and operations that are going on as they're installing the pipe. This is just an image of shaker type soil separator. Another shot here. This is actually a video, I think. So again, this is a separation plant and 3 different type screen shakers that are taking 3 different size particles off the top and falling, and these are transported away. This is a lubrication pump, very common in a slurry type microtunneling. They're pumping this into the slurry, as well as different types of materials are used for lubrication of the behind that MTBM. This was a project here that I was involved in. It was in Topeka, Kansas, and it was super soft ground and high-headed groundwater, as well as the jacking pit was right here in the center, and they tunneled to the left to a new pump station, then turned around the same pit, and then tunneled underneath this building that was built years ago. It was an old building built years ago over the top of these 2 abandoned clarifiers at this plant. So this is out to the right. This is that existing building T. So here's a sort of a profile view of what was above this installation. So you can see in the one direction, you can see all these utilities. I think there was about 9 utilities that we went underneath, going one direction, then turned around, and then came to the left. Underneath this building, the clarifiers aren't shown in this screen. So it was all 20-inch inside diameter pipe, all done by slurry type microtunneling. But you can see the reasons they chose microtunneling here, because of all these utilities, as well as underneath the building for this new sanitary sewer line. This is that building T right here, and behind this rubber tire picker is the jacking pit, and there's some sections. Those are 20-inch ID. I think they were 4-foot section lengths that what they supplied them. This is down in the pit, and you can see this is the jacking pit. This is a Whaler type cofferdam sheet pile shaft, and you can see, this is the shaft seal right here where the pipe exits. Again, high head of water. You got to have the whole shaft sealed off to prevent infiltration of soil into the shaft. This is the laser right here. This is the concrete thrust blocks that they poured, jacking frame, slurry pumps, and then these soft lines here going to the a feed and a return line. Here's the metering wheel that you saw in the video, and they're going. When I took this picture, they were going underneath that building T, and this pipe here, this end of this pipe, going to the right. This went to the new pump station. Another shot here, pushing pipe. Again, 20-inch ID, 500 millimeter diameter pipe. This was their soil separation plant. Hey, that's it for slurry type microtunneling. I'm going to cover our jacking pipe here in about 15 to maybe 20 minutes, and then we'll be through with the lecture. But again, like I said earlier, you know, I'd say 95% of the projects that we're involved with today are using the pilot tube method or pilot tube guided boring method. We're still doing a little bit of slurry microtunneling. We're doing some pipe bursting. I think you guys might have had a lecture on pipe bursting, and the same pipe can be pulled in behind what they call a static machine, but the pipe has to be restrained. It's designed to be cartridge loaded and pushed. And we can slip line casing with it, and we can also slip line existing pipe with it as well. But you know, if anybody knows anything about clay pipe, you know, it's what we make today is not what was made 100 or even 200 years ago. These pictures are kind of fun. I found them in one of the factories, but this is a picture of it's actually donkeys they used to transport pipe with. These pictures were taken. I'm not sure where the pipe was going, but it was made, but it was going to Flagstaff, Arizona, and I think they transported this pipe via donkeys probably 150 years ago. Another shot here taking that clay pipe via donkey to Flagstaff, Arizona. This was I found these at one of the factories too, but these were taken in Amarillo, Texas, back in June of 1927. But it was actually hand mined, and it was 18-inch bell and spigot pipe in 3-foot joints, and it was they had shafts every 25 feet. Something else, 27 to 40 feet deep. Yeah, lowering those sections of the pipe could have been the first tunnel project. So this was a little bit more recently in the same city of Amarillo. We had a slurry microtunnel project about 5,000 feet of 36s using our clay jacking pipe. But you know, that old pipe, as good as it was, it wasn't anything in a comparison of what's made today. If you guys ever want to go to building products, again, let me know, and I can set you up for a factory tour. It's kind of neat to see. But you know, as good as that old pipe ever was, even up into the early 1950s, they used steam to drive presses and extrude the pipe. That pipe was created day one with laminations within the cross section. What's made today, you're going to see from some of the videos I have, but you know, we make a tight, dense product that has a fairly thick wall, and you know, we have a compressive strength of about 18,000 psi. So when you team up that kind of compressive strength with a thick wall to generate a large end cross section, you can put a tremendous amount of axial jacking force on clay pipe. You know, our joint has really evolved too. You know, in the open trench market, we went from a hand or field applied type joint in the trench to a factory applied joint. The photograph on the left, that's he's pouring probably a tar joint. It was very common up until about the early 1970s. We were using tar or mortar for the joint of clay pipe, and neither one of those really survived longevity and corrosion resistance, or allowed for really any movement in that rigid product. Open trench pipe, we use a polyurethane. If you guys go to building products, you'll see the polyurethane joint that we use on bell and spigot pipe. And the jacking pipe it's really a different animal. It's got to be a flush joint to be pushed through the ground, and you know, the jacking pipe is a plain end pipe. Pipe barrel, no bell, and we machine both ends to allow for an elastomer as well as a stainless steel collar. This photograph was taken on a pilot tube project with a powered cutter head, and they staged the pipe with the hydraulics inside along the swing radius of the boom truck to aid in productivity. But to make clay pipe or open trench pipe, or brick, which is vitrified clay, or roof tile, or floor tile, or flue liners. Really, any vitrified clay product follows these same steps. The clays are mined, they're brought to the factory, and they're stored and they're ground. You know, their recipe or their blend, it all depends on where the factories are located. And some factories might have 2 clays that go in to make their mix, or some factories might have 5 clays and shale and slate to go in to make their product. Everybody's got a different recipe, you know, that's based off of the available clays that they mine in their area. The photograph on the right, that is actually in Phoenix at the factory. It's on Buckeye Road, just west of downtown. But that's extruding a 36-inch bell and spigot pipe. But the pipe are extruded, they're dried, then they're kiln fired, and they're jointed and quality tested. This is a video of what they call the pug mill. So this is adding water to the blend of clay. So in that video, the clays have already been mixed. They've been ground to a fine particle size, and they're adding water. And at that stage of the game, it's about a 15% moisture content. But it goes through the pug mill into a vacuum chamber where they pull all the air particles out of it, and then it's hydraulically extruded. So this is a video here. This is in Phoenix as well, but this is making 8-inch bell and spigot pipe. So once the pipe are extruded, again, they're 15% moisture content when they extrude. You know, if you go to the factory, you'd be fairly surprised at how dense that pipe is when it comes out of the press. And you know, once they're extruded, the ends are trimmed, and then they're sent into a drying room. And these are some large diameter jacking pipe in a drying room, and they've got to be dried to a 1% moisture content before they can be then transported to the kiln to be kiln fired. So this is some bell and spigot pipe being set in what they would call a periodic or beehive kiln. And this manufacturer, they're stacking these pipe too high. They're going to get as much product in there as they can, and then they're going to close the door and they're going to run it through the firing cycle. And kiln firing happens at 2,000 degrees Fahrenheit, and it turns that dirt, if you will, into a ceramic type material. This is a picture here of several periodic kilns lined up. But you know, today these kilns they're all computer controlled. Most of the plants are gas fired, and it's a gas burner and an air blower. And you know, the kiln process is going from ambient temp, slowly heating to 2,000 degrees, and all depending on the pipe size, how long they hold it at 2,000 degrees, and then cool down at that same rate. But it turns that clay into a ceramic, which of course has a long life and is chemically inert. But the jacking pipe, the Japanese and the Germans were making it longer than we have been. But we started development in about 1990 and came out with the pipe in about 93, I believe it was the year before me. But here's a shop drawing for an 18-inch jacking pipe. And you can see it's really it's a spigot pipe, and it's got a machined end. Both ends are machined, and then they grind a recess in both ends, and they apply an elastomer, and it's got a flange gasket here, and then this secondary gasket, they call it a filler, or you can call it a mud ring. And then every joint has a stainless steel collar, which is about 4 3/4 inch wide. And that collar slides across the end of the pipe. It makes it seal right here, and then it comes all the way to the end. So the secondary gasket, as you're tunneling, it keeps the dirt from getting down in here and affecting the seal. This is a photograph here of a jacking pipe being machined. So the jacking pipe are actually machined after firing. So they fire these clay pipe barrels, and then each section, whether it's a 2 meter or a 1 meter or a 4 foot or a 3 foot section length, they're all machined individually. And so those pipe are put on a lathe, and they're diamond ground, and the ends are cut perfectly square on that lathe as it's rotating. And then they machine the recess in both ends at the same time to allow for the joint, for the flush joint. This is a close-up shot of the diamond grinder. Again, grinding the recess in the end, as well as cutting the end for end squareness, which is a pretty key element to a jacking pipe. The jacking pipes have to be perfectly square on the ends, and our pipes are machined to within about 30 thousandths of an inch at the most for end squareness, which is pretty tight. It's a video here of making I think it's a 12-inch jacking pipe. Oh. So once the pipes are ground, if there's any kind of a fracture or a problem with the pipe, it would happen at this stage of the game. And so they inspect every pipe with a MagnaFlux, which is a material commonly used to check welds for any kind of fractures or any kind of problems. But they paint this MagnaFlux on both ends of the pipe, and if there's any kind of a defect that you couldn't see with the naked eye, it would show up with the MagnaFlux inspection. For elastomers, really the standard is a natural rubber, which is polyisoprene. Can use a nitrile or EPDM or even a silicone Teflon type gasket. But really what this hinges upon is, what's going to be flowing inside the pipe or what's on the soils outside the pipe is going to dictate the elastomer. We do a lot of industrial project applications, and the clay pipe can handle about every chemical known to man. But you want to pick the right elastomer for what's ever going to be inside or outside the pipe. Stainless steel collars, our standard is a 316 grade stainless steel. We're doing some projects in Hawaii or in the Seattle area where they're concerned about brackish water or salt water. So we're going to use a different type collar. It's an AL6XN that resists that brackish water better than the standard 316 grade stainless. So for pressure testing, we do a lot of deep applications with groundwater in microtunnel applications. So this is just an illustration of how we could test that joint from the outside with a pressure test. And we would put an apparatus around the outside of the pipe with a port and some elastomers here, and actually pressure test that joint from the outside. And I've went down and witnessed some shear loading and some pressure testing. And here's one that I went down and witnessed. It was actually for a pilot tube project where they dewatered, and it was they wanted that pipe tested to 100 foot of groundwater head. So this is a 24-inch pipe. This was a test apparatus on the outside, and we took that pipe to about 45, almost 45 PSI, which is equivalent to 100 foot of external head pressure without leakage. So axial loading during installation, with these tunnel methods, the greatest load that pipe will ever see any day in its life commonly would be that axial jacking force the day that they push it in the ground, because they're digging a hole just big enough for the pipe, and they're never going to see a conventional trench load on that pipe. You can compute it, but it's not much. But So how do you rate the pipe in terms of axial capacity? It's a fairly simple calculation. It's the ground OD from the ID. It's this cross-sectional end area of the pipe. So, here's just an example for 18-inch pipe. It's got a bearing area on that end of 110 square inches, and we specify the pipe to be minimum of 7,000 psi compressive strength, but there's a big safety factor in this number. But for computations and computing load, we're going to use this minimum number. So with 110 square inch pipe, we're gonna use 7,000 psi, and that pipe's rated for 384 tons. And then we're going to take it to another factor of safety of 2.5. So the published number for 18-inch pipe is 150 tons. This manufacturer makes up to 24. So using 2.5 safety factor, 8-inch pipe can take 45, up to 24-inch pipe can take 221 tons of axial jacking capacity. I did a research project with a group of seniors for their design project, and we tried to point load some 24-inch pipe, and this was at their lab at University of Illinois Champaign-Urbana, and this was a 3 million kip load machine that we used, and we had platens to push that pipe off center, and then we had these resistors positioned around the joint with no collar, so we can measure the deflection in the joint as we loaded it. And this pipe, we deflected it to a 0.16 degree angle of deflection using these resistors. And that pipe took 1,750 kips, which is about 900 tons of load. And again, this pipe was 24 inches, rated for 221 tons. And we point loaded it, and it finally failed at 900 tons. So earth and live load, I mentioned this earlier. You can compute this earth load on this tunnel pipe. I'm not going to get too deep in the math with this, and you can also compute live load. And live load could be a concern if you were shallower than about 8 feet. When you're shallower than 8 feet and you've got a live load, you can compute it. And here's a couple of examples here. I computed a 10-inch pipe with 28 foot of cover, and the live load was 676 pounds per feet on the pipe. And the pipe's rated for 2,400 pounds, so the safety factor is about 3.5. And then here's one with a shallow bury. I put an HS20 live load on it and computed that load to be 525 pounds per linear foot acting on that pipe. And same pipe rated at 2,400 pounds per foot. The safety factor is 4.5. Lube ports, we don't do this too much in pilot tube, but for slurry tunnel projects, these pictures were from a pipe burst that we did actually in Phoenix area. But we could put lube ports in the pipe, and these would have to be accessible after the pipe was installed, where they could go back in and plug those ports. But this is a cord hole in the pipe, and using a ceramic epoxy, and you can attach some threads in there, and then pipe lubricant to the outside of that pipe during installation. Hey, a little bit about clay pipe, for those of you that aren't aware, but why would somebody want it where you guys are? The city of Phoenix uses clay pipe in the sizes that we make for open trench installation of gravity flow sewers. But why would somebody want it? It's got really unmatched maintenance in terms of abrasion resistance and what you can do with it in terms of maintenance and cutters and jets and pressures. It's a rigid pipe. It's 100% natural. What goes in to make clay pipe is mined clays and shales and slate. It's 100% natural, sustainable. It doesn't burn. We've got this. Now we have this leak-free, root-free, flexible compression joints, corrosion resistance. Nobody can match what we can do in terms of what will corrode clay pipe. We're 100% inert, and we're a kiln-fired ceramic, so we don't we don't change properties with time, and that's something you can't say about a whole lot of construction materials made today. But you know, our biggest competitor really in the open cut world is PVC pipe, and you know, PVC degrades over time, whether it's in the sun or whether it's underground. So they can't match us on longevity, and they can't match us on maintenance either, as far as cleaning tools, which is a big deal for gravity flow sewers. You know, here's just a couple of examples on the maintenance side. This was 2 4-inch pipes, and you know, using a hydrojet cleaning truck, and running at 60 gallons per minute at 2,000 psi for cleaning. And you can see the damage to the clay pipe after 5 minutes of jet pressure hit the outside. And the 4-inch SDR35 PVC pipe, there was 3 holes in it after 10 seconds of use. So here's a couple of videos here. I got these from the city of LA. This was an 8-inch main that had a lateral connection right here with a big root mass coming in. So this is before. And this was after the root saw went through it. So this is, again, an 8-inch pipe, and they're 265 feet in that pipe from the manhole where they set the camera in. And you see this root mass coming in. This is actually a plugged, there's a PVC cookie. It's a capped off lateral that's undoubtedly.
We got a cap lateral with severe root system in the lateral, 265 feet, first quadrant.
So, you know, that's a capped lateral that's undoubtedly not capped well enough to keep the roots out. So this is same pipe after they ran this root saw through there. So that pipe is clean up inside that lateral. So this is the tool they ran through there. That's a 3-bladed saw. It's a hydro powered, so it, you know, a city truck can power that thing, and it's got a rear device back there to clean as it goes. But you know, you can't use this in the flexible plastic type pipe. So you know, this situation, if it would have been another type of pipe, it would be a dig and replace most likely. Otherwise, they would damage the first 265 feet of this other type pipe to get to the problem. So here's another one. This is another lateral right here where the homeowner had somebody come in and line it, but the liner extends into the main. So you can see where it's catching the paper right here. But this is what they call a hydromechanical tool. This is a can cutter. So this is it can be run on a jet truck as well. This is a can cutter sized about 7.5 OD running inside this 8-inch pipe, 8-inch main. You can call it Sparky if you want. It's running down this clay pipe, and you can see all the sparks it's generating. They solved the problem there. Then they almost took out their camera guy at the other side. But you can't run that in a flexible pipe either without fear of eating the top out. Hey, I got about 3 slides left. How are we doing on time? We're pretty close. But we've done a bunch of pilot tube work up in Minneapolis, but they're a big clay pipe user for open cut. But I was up there on a project. This was 2017 before the Super Bowl. They were revitalizing this area, and this pipe was undersized, so we were pilot tubing, and we had a big jacking shaft at the corner here in Nicollet and 12th Street, and we were parallel installing these new 15s and 18s next to this existing pipe. The existing pipe was in perfect shape, but it was just undersized. And later, I got this as-built from the city, and this pipe that we were abandoning was 12-inch clay pipe, and we had several pieces where they were right here within this jacking shaft that we retrieved. We sent a couple of them back to Logan Clay in Ohio, and we actually bearing tested those pipes, and those pipes, we pulled them out in 2016, and they were actually installed in 1896 according to this as-built. It was built in 1896, so the pipe, you know, were installed, or they were built, they were made, installed, and in service for 120 years. And then we bearing tested them in 2016 at Logan Clay, and those pipe broke at 42% above the ASTM. You know, they didn't degrade over time, and you know, they were only removed from service because they were undersized for what they were building there in downtown Minneapolis. Hey, that's what I got for you guys, and I finished, I guess, just right on time here within a few minutes to spare. Any questions for me on